I'm going to talk today about topological data analysis and what we do at Ayasdi. So I have kind of two goals here that for this talk. So first, I want to show how TDA is a framework for data analysis or machine learning. Sort of, if you think of machine learning just as large-scale data analysis, and then I want to demonstrate specifically how Ayasdi uses TDA to help companies. And so at the end of the talk, I'd like to show you some of the actual some actual use cases from some of our clients. And so TDA encompasses a number of things, and I'm really just going to talk about the part of TDA that Ayasdi does. So there are other things that I'm not going to talk about: persistence homology, sensor networks with sheaves, things like that. But that's fine. Okay, so what we want to do is extract meaning from complex data. So we want to get insights from our data. We want to make our data useful. And I say complex because, well, data is complex because it's big, meaning there's a lot of it. So that's one way data is complex, and we deal with some of that at Ayasdi. But we also deal with a lot of data that's complex because it's feature rich. So if you think of something like genetic data, you could have SNP data, you could have 500,000 columns in the data set, and there's complicated interdependencies among those columns, among gene expression levels, among mutations, among all kinds of things. And so I don't want to think of the data problem as just being one of volume. I want to think of complexity, and complexity can come from volume. It can come from other problems as well. So, or of course both, right? You can always have both. So the way I see the problem in both cases is that there's a lot happening in your data. So a metaphor that I like to think about is that of a room. You walk into a room full of people, and when you walk in, it's just white noise, right? There's all these different conversations happening. And what you want to do is find those conversations that are relevant to you, or in some way summarize the conversations in the room. So that's the problem with big data and with complexity are the number of stories going on. And what we want to do is create summaries that are useful to us. So TDA on this kind of high level, this metaphorical level, is the tool that's going to summarize out the irrelevant stories to get at something interesting. And in a certain sense, I mean this in a kind of technical way, because what we do is actually we summarize the geometry, and we do that in a rigorous way. So the metaphor is reasonably deep. Okay, so this here is kind of our guiding principle at Ayasdi, is that data has shape and shape has meaning. That's the motivation for everything we do. That's how we try and approach our problems, is what is the shape of our data? How do I extract the shape of the data? What is the shape of the data? Tell me. So I'm going to focus on the second half of this and not get too much into exactly what shape means. I want to talk about extracting meaning from shape. Okay, but first, well, let's just since I've gotten this question before, well, what is shape? Let's just spend a slide describing what shape is. So I describe shape as like my one sentence that I use to describe shape is that shape is the global realization of local constraints. So locally, there's in your data, locally in the space you're looking at, there's some constraints over what can happen, right? But those local constraints sort of doesn't really create shape. Shape is what happens when you take the big picture of all those constraints, right? If you look at a circle, locally it's very flat, it looks like a line, but it's bending ever so slightly. When you take that global picture, you get the circle, and that's the shape. That's the shape of your data. So for a given problem, shape is determined by your choice of features, sensors that you're pulling data from, columns in your data, if you're thinking have tabular data, properties to measure, and then a metric on those features. So that metric is the summary of what those local constraints are. So that's one way to define shape, but there are more relaxed notions of shape. And the techniques I'm going to describe to you today are going to work with those other more relaxed notions. So everything, I'll probably say this a couple more times, everything I say will work for essentially abstract topological spaces where you have some open covering of the space. So you have a set of open sets that cover the space. But to stay concrete, everything I say will be done with rows and columns. The rows are your data points, the columns are your features. There'll be a kind of metric lurking in the background, and we'll just move and stay in that sort of concrete, more familiar world. So the goal, this is just rephrasing what I said earlier, it's to understand or summarize the shape. And part of that that's really important for TDA, which is what I think distinguishes it from a lot of other techniques, is that we have no preconceived notions of what the shape should be. So we're not doing any kind of like manifold fitting or linear fitting or anything like that. We really try and eschew the preconceived notions of what our data looks like. Okay, so I'm going to kind of step into the TDA in a couple steps. So first, I'm going to start in math world. So we're not in data world yet. So what do I mean by math world? I'm going to draw the data as a smooth manifold. So it's just going to be a smooth shape. And when I say function or lens, you should think something smooth, continuous, nice in whatever class of functions you want to consider. So that's because that's going to give you the right intuition and kind of internal mental picture. But we don't need any of these assumptions when we're actually in data world doing the analysis. All the things that I'll describe will go through without modification. Okay, and maybe even more importantly is that in the real world, data is never really sampled from a smooth manifold. Or I should say, there are certain engineering problems that are very rigidly constrained where data might be sampled from a smooth manifold or from a, maybe just a locally smooth or, stratified space or something. But in general, real data is never like this. It's kind of crazy and wild. And we should keep that in mind. Okay, so here's our data, and I've drawn here, it's an inverted pair of pants. And when I produce here, I'm going to now kind of flesh out this picture, and I'm going to show you how we make topological summaries from the data. But you should remember that you never actually get to see your data. And the reason I'm drawing it as this nice two-dimensional manifold is so that you can concretely see exactly what is the thing that I'm summarizing, what is the topology, what have I lost, what am I saying, right? Well, you'll be able to see it all exactly, but in reality, you never get to see it. So you should put kind of a big black box over the data. Okay, so here's how we start. We start with the continuous function f, and this function f at Ayasdi, we call it a lens on your data. And I'll probably switch back and forth between saying lens and saying function, and you'll just have to bear with me. I apologize. I've been sort of indoctrinated into the corporate language. But it's just a function, and you should consider it a smooth function. So here's what we do. We take a point P, and here the way I've drawn it, I'm thinking of this function as just the height function on this data. So I take a point P in the range of the function. I look at the inverse image of P. So that's this circle here. I take that inverse image, and I'm going to draw a point on the far right here for every connected component of the inverse image. So the way I drew this here, there's just one connected component. There's just a circle in the inverse image. So I drew a point on the far right. Okay, so let's look at the point Q. Now we have two circles in the inverse image, so there's two connected components. So I'm going to draw 2 points. And that's it. That's all we're going to do. And I just go through all the points now, systematically do that. I get this y. So this is a summary of the data space. So the data space started off as this pair of pants that has this hollow cavity. And with this function, the summary I've produced is this y. What have I captured? I've captured the legs on the pair of pants. What have I lost? Well, I've lost all the holes, the circles, right, with this function. So that's one choice of function. Well, now I'm going to look at another function to show you how other functions will extract other summaries from the data. So this function is just this function that goes down, g. So p, look at the inverse image of p. It's this left edge. And so I'm just going to draw a point for that left edge. Moving slightly to the right, I have two pieces in the inverse image. There's this front line and this back line. So continuing on like that, I get a circle until I reach this middle point here, where again, the inverse image of a point in the middle is kind of the saddle point here. It's connected. So I just get over that image a line. And then on the other side, by symmetry, I'm going to have a circle again. So here's my second function, and this is my second summary, which is I've captured now something completely different about my data. I've captured the fact that there are two legs. There are two leg holes. So different functions are creating different summaries. This is it. This is what we do, and it's surprisingly useful and powerful, and yeah. So I guess all the best ideas are really simple. I think that's fair to say. Okay, so we have the two holes for the legs, and we have the leg-like structure. Okay, so since this is a course, I thought I'd have an exercise for everyone, which is what happens if I use both lenses at the same time? So both functions, g and f. I wrote g and f and not f and g because g was the one with the x direction and f was the one with the y direction. So what happens if I use both functions at the same time? So the image now is the range is two-dimensional, and I want to take a point P in the range. I want to take the inverse image of P, take the connected components of the inverse image of P, and then let P range over the whole range. So I'll just give everyone a minute to think about that. If you solve it, you should raise your hand and tell us the answer. If you know the answer, which I know there are some ringers in the crowd, you may not answer. Any takers? Okay, it can be hard to do in your head. So let's just step through how to do this. So it's an exercise, I guess, only if you stop and do it. So P has the inverse image of P from F. F inverse P is the circle. It's right in the middle. So the inverse image from G is that saddle loop. And I take the intersection of both of those to get the inverse image under both G and F simultaneously. So the inverse image of P under this combined map consists of just 2 points. So when I draw now, right, those 2 points are two connected pieces. So that means in the output step, I would draw 2 points. Right? Now what happens? As P moves around, right, if you imagine P just shifting left and right, the saddle piece, right, moves this way. If P goes up and down, I'm moving the ring up and down. And at most of those points, I'm going to get 2 points in the inverse image. Sometimes I'll get 4. Sometimes I'll get just 1, depending if it's right on the edge. But in any case, what you can convince yourself of is that we recover the space that we started with using this procedure. Okay, that's great. That says that we don't have to lose information. So this topological summary doesn't have to lose information. We can recover the space itself. So with a rich set of functions, lenses, we recover the original space with this procedure. Well, I mean, that's kind of a non-starter. The original problem was that the original space is too complicated to understand. There's too much going on, so that doesn't really get us anywhere. But it does say we can select the functions to tune to the signal we want, to tune into the conversation we want. We can, so by selecting the functions, we can choose what information to get rid of and what information we want to keep. Okay, so here we are again. For the second time, this is what Ayasdi does. We produce summaries. By choosing the functions, we choose what we're summarizing, and we can keep as much information as we want, or we can eliminate as much information as we want. Okay, well, that's what we do modulo some details. So why is this useful? One of the most common tasks that we do at Ayasdi with our data analysis is that we look for localizations of some quantity of interest. So if you're looking at online transactions, you're looking for the transactions that are fraudulent. If you're looking at gene expression data, you're looking for the people who have cancer, right? So we're interested in certain subpopulations or certain subsets of our data, which is sort of what I put under the word localization. So this is what we're looking for. Is we're looking to understand what is the test, what are the genetic tests for this kind of cancer, or whether we should treat this patient with this kind of drug, or whether we should flag this transaction as fraudulent. Okay, so here's our summary again. So here's one kind of localization. Those red points up there, those are the people who are committing fraud in our data set, or those are the people who have cancer. Well, what happens to them under F? Well, they all end up over there, right, on that little piece of the Y branch. So you can imagine if this is, if this is gene expression data, I have the original space has thousands of dimensions, but my summary has only, right, it's just this Y, it just has really one dimension almost everywhere. And I can just look at it now, and I can see where those cancer patients are, where those fraudulent transactions are, and that gives me the ability to, I know now where to go look at my data to find the things that I'm interested in. Well, this here is a particularly easy kind of localization. Maybe I'm trying to distinguish two classes of objects, right, red and blue. Well, this is a little bit harder because over here now we have purple, right, with F. Red and blue get mixed, and I can't separate them out using F as a lens. Well, luckily, we have two lenses here. I can use G. So this says some problems, like here, so some problems are easy. Finding the red, almost any continuous function is going to localize that red for you in the output. Right? You have to sort of cook up some very strange function that's going to spread that red all over the place. Almost all the functions. So finding that kind of, maybe it's like a classical clustering problem. There's just kind of, a compact set in your data that's of interest to you. And maybe there's lots of other techniques you can use to find it as well. And for us, I'm just saying, yeah, we can do that too, and it's not hard. But there are other problems that get easy that require maybe a more refined choice of lens. Okay, so here's where things get interesting. What if the things that you're looking for are themselves have some complex geometry inside of your data set? So here, my complex geometry is this just smeared out set of points, right? It's not in a nice, small ball region of the data set. It's spread along some dimension. It has some shape in the data. Well, F says it's kind of almost everywhere. So F isn't particularly useful for finding its localization. But again, G is very useful. It says, oh, all that stuff, all that complicated geometry that it might have, it gets summarized into, it all lives right here in your data set. Yes?
So all these operations are very similar if you just do like standard manifold learning, like the local linear embeddings or isomap. How are your algorithms?
So, okay, so good question. So one is, which I tried to mention earlier, that real data never has any kind of manifold structure. So I've drawn manifold, but like, forget it. There is no local manifold in like real big data sets. So that's point one. So isomap can sometimes do this, and sometimes not. So I'll show you later how we can use isomap as part of our system. And in fact, that's something that we do. So for us, isomap becomes just another lens, another function. So isomap, all those techniques, those kind of dimensionality reduction techniques, that's part of the framework part of this talk. They all will fit in here as lenses. So, or PCA will fit in as a lens. And that's something that I'll describe a little bit later in the talk. The thing that you lose when you look at isomap, so is you don't understand, right, the dimensions that you've lost, right? Sort of how they've been pressed down into that representation. You don't know if they just, like with isomap, it would be like projecting just to the line, but forgetting about the fact that the legs are separated, right? If I did an isomap, a one-dimensional isomap of this pair of pants is going to just go, that's unfortunate. It's just going to be the line.
Sure, but you could do 2D isomap.
Right, but the point is that the data, as I drew it as two-dimensional, but you're supposed to think of it as a million-dimensional. Whatever, right? 1,000-dimensional. You can't, right? Doing a 1,000-dimensional isomap defeats the purpose of doing isomap to some degree, right? So, so one way of thinking about this is that we share some things in common with a tool like isomap or MDS or TISNI or something like that, except we remember something about the fibers of that map. So that's another way of thinking about this. That remembering that Y is remembering the fibers. Okay, so lenses inform us on where to look in the space for phenomena we're interested in. For easy localization problems, many different lenses will work, and we see that a lot. Sort of no matter what you try, you'll see the localization. For hard problems, which hard I mean geometrically distributed in the space, localizations, we have to be more careful about what lenses, so we'll have to do some work to figure out what lenses are appropriate. But even then, we can get incremental knowledge about the problem from even a poorly chosen lens. And by incremental knowledge, I mean if we go back here, right, even this bad lens, I'm able to eliminate that arm as a place for the green points. So I get some incremental knowledge even from bad lenses. Okay, so this is our math world. And now I want to show you how to take this and translate it into data world. So we're going to move from this world of nice, smooth manifolds, continuous functions, into a data-driven analysis. So the first thing we want to do is replace points in the range with open intervals. Well, in the data world, no matter how big your data is, you always have a finite number of points, which says that for a randomly chosen point in the range, its inverse image is empty, right? And then when I try and do this sort of just ranging over those inverse images, drawing points and connecting them, I have no way to connect them because I get a point and then I get mostly a bunch of empty inverse images, and I get a point, maybe I get 2 points, right? So I fatten up those points into open sets. So I take an open covering of the range of the function. Now I again take inverse images of those open sets, and I'm going to also continue with, I'm going to take connected components of the inverse image. I'm going to draw a dot, but now this dot, right, represents a lot of points. So I do a big dot. I do that. So that's the inverse image of U1. It's just this kind of cylindrical piece at the bottom. It's one connected component. It gets one dot. U2, it's again still one piece. It starts up the legs, but it's just one piece. And I get another dot. U3, now I have two cylinders in the inverse image, so I get two dots. And I'm going to connect nodes when their inverse images intersect. So U1 and U2 have an intersection, so I connect them. And U2 and right U3 have an intersection, and U2 and left U3 have an intersection, but left and right U3 have no intersection. So the output is now a graph. So the output before for a single lens was a curve. Now the output's going to be a graph.
Shouldn't the dots be varied in size? That's the whole point of making one of them big.
No.
There's fewer, in the two upper components, there's fewer data points.
That's right. So, well, in this case, I mean, if we want to get technical, in this case, it's a continuum. I've got the same number of points in all the pieces.
But you said you didn't.
But
real world data isn't
that's right. So, what you say is a good suggestion. It's something we could do, and it's something we do in our software. One of the options that you have in the software is to size the points by the number of data points they contain. But you may want to size them by something else, right, for some other visual effect. So I don't want to set that as like part of the core algorithm. Okay, so as part of this construction, though, I've introduced some more parameters. So before, there was sort of a unique, right? You give me a data set, you give me a function, then there's this unique output, right? Data set function, there's the unique curve according to the procedure. Now, because there's a question about how many open sets are you going to take, how big are they, what is the overlap? So there's some parameters, unfortunately, that come into the construction. So the resolution is the number of open sets that we have in the range, or the size of the number, if you're thinking of just a one-dimensional set, really the size maybe of the open sets. And the gain is the amount of overlap they have between their neighbors. So roughly speaking, the resolution controls the number of nodes in your output, the number of nodes in your graph, and also the size of geometric feature that you can pick out with the procedure. While the gain controls the number of edges in the graph and also the tightness of the graph. It's a little bit more complicated to go into kind of technical detail on tightness, but just resolution is pretty straightforward to look at. So if I took 4 open sets instead of 3 open sets, right? Well, I basically get the same thing except with just an extra node now inserted. That's because for this lens direction, that y, right, is already the maximal information that I can really extract, right? I already have, if you think of it as the resolution goes to infinity, I should approach the curved version, right? The line, the y that's a line, right? And with 3 sets, I already had the y. So I'm not, no matter how high the resolution goes, I don't really pick up anything more in this case. Well, if I drop the resolution to 2, I lose the topology. So the minimal amount of information you can recover is just the set of function values that you have. And that's just in this case represented by a line. And that is actually, in a lot of problems, enough for us. For a lot of problems we look at Ayasdi, even getting just the line, or as some people like to call it, the worm, it's enough to solve a problem. For instance, if you imagine a sort of if I'm looking for something in the upper half of my pair of pants, they would all end up in the upper node, and now I know where to go look. Right? So even the minimal information recovered is itself useful and interesting in a lot of cases. Okay, so that was step one, was to look at these open set coverings of the range. Now, connected component, if I have data points, right, they're all sort of by themselves. The notion of connected component doesn't make sense. So I want to replace connected component with something that's going to work in the data world. And so the way I do that is I'm going to cluster within the inverse image of an open set. So clustering is data pi naught. So before, we connected the nodes when their inverse image open sets intersected. Now we've gone to this clustering, and we're going to connect clusters or nodes when they share points in common. So there's these inverse images, they have this band of overlap, right? And there's some points, say, in that overlap. When I cluster the bottom set, those points go to one set of clusters. The top here, I'll just stop trying to explain it, and I'll show it to you because I have a nice illustration. Picture's worth 1,000 words, and I was heading to 500. Okay, so here's our data world where we have points. So I take this U1, I look at its inverse image, and I do clustering, some clustering algorithm, whatever you want. I'm not particular. I'm saying that I get 2 clusters in that inverse image. I go to U2, which is this set. I cluster. I get 2 clusters. Now there are points that are in both U1 and U2. Those points go to some clusters in the bottom set, and they go to some clusters in the top set, and I'll just connect those clusters. Which I'm saying, this isn't like a real problem. I have no idea where the clustering would send those points. But I'm saying that this is what happens. Okay, so now I just continue this process. So remember, nodes are now clusters of data points. Edges represent shared points between the clusters. And we just keep going up. And we just do this to the end. I gave you the preview. So that's now, we get this more complicated graph as an output, but it still contains the same essential information as before, which was this Y structure that the lens was picking out of the data. Okay, so that's it. That's the full algorithm. Well, of course, again, modulo some details. I haven't said what clustering we've used. I haven't said there's all kinds of implementation details, right? Maybe you're wondering about how we store our data tables and how we access things to do this in a big data efficient, right? So modulo all the stuff that would make this useful, that's what we do. Okay, well, again, that's not quite what we do. Well, what about the lenses, right? The whole technique relies on these lenses, right? Where do you get your lenses from? These continuous functions, right? That's what's pulling the information out of the data. That's what's creating the summaries. So we need to find good lenses. And lucky for us, we haven't had to do this on our own. So people have been coming up with lenses for hundreds of years. They just didn't know that they were coming up with lenses. So here's a non-exhaustive table of lenses. So statistics. Anything that produces a number for a point is a legitimate lens. So if I think of a point as being, a row in a data matrix, I can take the mean of the values in that row, the max of the values in that row, right? Variance, nth moments. I can take the density using some kernel density estimator, right? The density is a value at a point, right? Anything that gives me a value at a point is a lens. So this here is where our framework starts to come in. We take all this existing data analysis tools, and we just say, nice, thank you, lenses. Well, lenses also come from geometry. One of the ones that we use a lot is centrality, which is also distance from the center of mass from your data. It's a good way to look for outliers or anomalous behaviors in your data. And it's not quite distance from the center of mass because we work with abstract metric spaces. So the center of mass is a little tricky, but centrality is a proxy for that. If you have a smooth case, which you never do, but if you did, you could filter by curvature, if you had some notion of local curvature. Harmonic cycles, so there's a way you can look for circles in your data set. So instead of the image being the real line, your image space can actually be any other topological space that has an open covering. So the lens can go to circles as well as it can go to the line. So like we said here, so we already mentioned isomap, MDS, TSNE. These are dimensionality reduction techniques. So what do I mean when I say that's a lens? Well, that's you get coordinates. Let's say you do a two-dimensional reduction, right, to the plane. You have two coordinates. Each coordinate, right, is a lens in our view. You could do something like an autoencoder. So this is a different kind of lens. So I really like these other lenses. I'm not trying to bash neural networks or anything like that, but I really like these other lenses because they have intrinsic meaning outside of the problem that you're looking at. And that means that they're not really subject to overfitting because they don't fit the data, the data fits them, right? I mean, when you calculate the mean, you just do it. It has nothing to do, you don't fit the mean, right? You just calculate it. So if you're going to use a function that you fit to the data in some way, you have to be more careful, right? Overfitting, right? There's a whole literature and careers made out of understanding that issue. You can also look at something like distance from a hyperplane in an SVM. That's a nice function. It gives a real value for a point. A very good one for us as a use case is some kind of error information about your machine learning system, because we can very quickly look for systematic errors, systematic deviations within the system. And then the other area is domain knowledge or data-driven lenses, right? So you can just think of this as any column in your data set is a legitimate lens to use, because it's just a column just has a point, right? Has a value for every row. That's exactly what a lens is. So you can either use lenses that you use columns that you used in the analysis, or maybe even more interestingly, you use columns that you didn't use in the analysis. So my example there is like you're looking at, demographic information. You could use age as a lens, say, or if you're looking at something that happened in history, you can use dates as a lens. Okay. So I still promised you a discussion of insight and meaning. So I've showed you the summary, but where's the insight, right? What does it mean to get meaning from the data? Okay, so I claim that these lenses actually sort of generate insights for you, or they generate understanding of the data in a fundamental way. So here we have our complex data. Now I've blocked it out so that you can't see it, right? But we have our function f, our lens, and we have our summary, our favorite summary, which is the y. So let's say f is Gaussian density. So I'm filtering the data by a kernel density estimator. And let's say this is low densities at the bottom and high densities at the top. What does this summary tell me? The summary says my data is bimodal. There's two high dense regions, and there's a a low dense region in between the two. So if this were, if my data were like, say, cancer patients, this would say I have 2 types of cancer, right? So the units on the lens give me some interpretation of the output, allow me to get an insight, get new sort of knowledge from my data. Let's say F is centrality, and here I have my core is the bottom of the Y, and then I have 2 flares going out. If this were cancer again, it would say you really have 2 populations of cancer. Right? There are sort of 2 different ways of being out there and having cancer. You don't, maybe it's breast cancer, but there are 2 kinds of breast cancer. Right? But they're rare because they're far away from the central core. If F is mean, right, let's just say, I have sensors of some sort. This would say that when the sensors are high, there are 2 different ways that they're high. Right? So the units on the lens give interpretability and meaning to the topological summary. So we learn something. We don't just produce a summary that we say feed into, it's not really a black box system that just produces some kind of classification result for us. We actually learn something about our data, something in our guts about our data, some understanding of our data that we didn't have before from the units of the lens and from the geometry that we see in the output. Yes?
So you've got this collection of lenses which you can apply to a set of data to produce effectively one set of data for each point, for each lens selection. What if you take the vector of all of the lenses and then run it through the system again? What do you get? Do you get a way of looking at what the relative advantages of each lens are against a particular data set?
So I have a couple answers to your question. One, I filed a bug request to do exactly that in our system. Is I'd like the ability to essentially re-embed the space via, all of the lenses. So I think that that's something that's potentially useful. It's not something we've done a lot with. So that's like one answer to your question. The other one is sort of, I don't think you directly get a measure of the quality of the lens. I mean, you can look at them all individually, but there's you really just, you're left with the feature selection problem, and there's lots of ways of doing feature selection on data. So I don't think there's it's not like a freebie. If you just do all of them, then you can, you still have the feature selection problem to do on that set of outputs.
You have a tool for looking at the quality of
That's right.
a given lens at a given time.
That's absolutely right. Yeah. From that perspective, the system can help a lot with feature selection. Yes. Okay. So how's everyone doing? Okay. Another way of thinking about lenses, which I think is useful specifically for the lenses you want to construct yourself, like a data lens, is that a lens is a kind of geometric query of the data. So let me give 2 examples here. These are entirely concocted examples. So let's say you want to study heart disease. So you have a bunch of hearts, and you make all kinds of measurements on them, the size of various ventricles and arteries and the muscle mass, and right, you get all this information about the hearts, and so you have this big data set. So one thing you could do is you could just analyze, sort of globally analyze, try and globally cluster are there different kinds of heart disease, right? Or you could take a lens, like say age, and if you use the age as a lens, you'll spread out your data set over that age, and then you cluster above, right? Above every age, you're clustering independently. And so you're saying, how does heart disease express itself as a function of age? right? So it's a way of querying your data, and it's a geometric query of the data. And the stratification, you don't have to say, I'm going to look at people of this age and that age. Because of this way of binning and overlapping, you get a kind of continuous understanding of how the heart disease varies with age. So there's a geometric way of querying your data and understanding how does it vary with respect to my lens, with respect to the output of my lens. And another example, so this is something I worked on, which is heavy machinery and a bunch of embedded sensors. I used mean and variance of the sensor output with the sliding windows as a lens to look for operating regimes that could lead to failure. And so this was a collection of 250 sensors. So the data is 250 dimensional. And I normalized them to make sensors comparable because they were measuring different things. And what I found was with this query was that there were there was a high mean, high variance failure, and there was a high mean, low variance failure region, and which were actually not quite at the highest mean. They were sort of both kind of a little bit away from the highest mean for the failure for these machines. So this sort of, though, the analysis was constructed as a kind of query against the data, right? Because of the sensors, and I had some idea that mean and variance of temperature measurements could be something.
So you also have the mechanism for taking the heart disease case and sort of inverting it and do the stratification by disease type or some indicator of the disease and look for clusters of age.
That's right. So that's something we do a lot is, so there's an aspect here, and when I get to the live demo, I can show that to you, where we sort of color, right, networks by functions that weren't used as lenses and that weren't used as part of the analysis. And if that function varies in a nice way across that network, that says that you've sort of, the network has sort of good predictive powers, or it tells you something about that function. And I mean, that's sort of, it's a function that wasn't used in any way in the analysis. And so the way that's reflected in our software is via coloring. So coloring is just a proxy for function values on the graph. So yeah, and so that's something we look for a lot is we want to say, you know, could you predict age from looking at someone's heart, right? So you would build a network out of all the heart, you know, the heart measurements, and then you would color by age, and if it kind of goes, you have sort of young and old, and they sort of, you get this nice smooth variation, then it says, yes, the heart information is a good predictor of age. And then you can reverse that process by placing points into the network. Okay, so generalizations and extensions. So the way I've described it is really not, so the technique exists in much greater generality than how we've been discussing it and describing it. So one, metrics. We don't need a metric at all. So just the notion of similarity will do. Or maybe if you just have some way of clustering the data without any other notion, you can just use that. So we don't really need a metric. So lenses don't need to be continuous. So I had said before, just think of a continuous function. Lenses don't need to be continuous. I don't want to say exactly what they need to be. What they need to be is sensible, meaning they should have some meaning for the data set that you're looking at. But we don't have to define exactly what that means. And using lenses that are discontinuous, meaning, you know, that are, say, they take values in a finite number of categorical information, is itself very useful and something we do a lot. So lenses don't need to be continuous, just sensible. So, and I don't want to define sensible. It means, well, sensible. Don't take a random function, right? Have it have meaning for your data. So we saw that in the exercise, but I just wanted to stress it. You can use, if you use one lens, your output is a one-dimensional object, but you can use multiple lenses and your outputs will sort of have higher dimensionality, and we do that all the time as well. You can map to spaces other than R. So all we needed, we're using the lens to kind of slice up our data in a certain way with these inverse images of opening sets. So you can map to any topological space that has an open covering created in some way and use the inverse images and that works fine in the system. There's nothing we use that's special about R. And in fact, we don't even really need lenses at all. All we need is an open cover of the space. Right? So that's like the topology when we, if you want to say, well, where's the topology? Well, topology, open cover. Right? All we need are open covers. So the input space can be anything with a topology. So we work a lot with row column data. It's just tabular data. Rows are the points, columns are the features. But anything with a topology on it can work. And in particular, I just want to say that graphs are perfectly legitimate. To input a graph into the process, into this machine, the thing that you'll get out at the other end will be potentially another graph that has this sort of completely reshuffled and reorganized the graph that you're starting with, right? So it's a transformation from graph to graph, but it's a very complicated one that you can do. And then finally, so I've been saying that the output is a graph. Really, the output is an abstract simplicial complex, and I've totally sort of just swept that under the rug, sort of how the higher dimensional simplices arrive, where they come from in this picture. And I'd rather not get into that, but the actual output is an abstract simplicial complex with higher dimensional simplices.
How do you know the topology without a map?
So you can just define, I can take, 3 chairs, and I just say one open set is those two, one open set is those two, and now we're good. We have a topology on those 3 chairs. So there's no metric. I don't need a metric. It's a finite set. I just say group those like this, group those like that. That's a topology.
I think that's
Do you have a
pretty close to
closure property? Is the union of 2 open sets an open set?
So we actually don't really have to care about. So if you want to run through the math, right, of like open sets, and you create the nerve of the covering, that's sort of the world that we're talking in, then, you have to follow these kind of technicalities. But in the world that we work in, there is no, right, open set, well, we have data points, we have finite sets, it just doesn't matter, and the kind of details aren't important for the data side of the picture. They're important though. I mean, these kind of details are kind of the motivation for the technique. Thinking about nerves of coverings and check complexes and all these things motivate the technique, and they tell us where to look and how to frame what we're doing. But in the actual sort of running through the details in the finite set data world, it's sort of not. It's not an important quality. Okay, so. I work at Ayasdi. It's a software company, and we produce software that does this for you. So I wanted to show you our software. Okay, so this is one data set, and these are 4 different outputs using different lenses and metrics of that one data set. So I'm just going to focus on this one for a moment.
How many dimensions? How many points?
Okay, so this here is a small data set. So there's 272 points, and it's almost 1,600 dimensional. 1553. It's 1,553 dimensions. So this here falls into what I would call the complex data, right? It's not big data because there's a lot of points. It's gene expression data for breast cancer patients. So it's complex because there's, when you're looking at the expression of a gene, right, they're tied to each other, they're related to each other in complicated ways that you maybe can't model from first principles. And they're also, there's a lot going on in the data that has nothing to do with breast cancer, right? In this particular study, we want to know about breast cancer. Again, this is the sort of complex data problem. But there's regular things just having to do with normal cellular function in the gene expression data that has nothing to do with breast cancer. So you want to have a summary that gets to the issue that you're interested in. Okay, so this here, this is our network. So each node contains multiple patients. Right? The columns are gene expression columns in the network. And I have a Y. Right? It's not a coincidence that my whole my whole presentation was like focused on around the y. So in an actual data set I'm showing you, we get that nice y. So my metric up there is this blue highlighted one at the top where it says correlation plus centrality. My metric is correlation, so I'm looking at correlation between the columns as the metric. Sorry, between the rows. And my metric is centrality, which is this distance from the center of mass. And the way you should read this data set, let me just actually, the way you should read this data set is that these are points with low centrality. So those are points at the core of the data. And as you go out, moving away from the core, at some point, there are sort of two different ways of being anomalous in this data set, of being far out from the core. So when I look at this data set, if I just put this in and this comes up, immediately the geometry starts giving me questions to ask. And in this case, the obvious question is, well, what's going on at the edge? Why are there these two groups at the edge? So what I can do is I can make two groups, which I've already done offline. I wasn't sure if I had was going to have internet access. So all the processing is done on our server. So I actually this is like a semi-live analysis because I've actually already done everything. Right? So I apologize for that. So I made two groups, and I've titled them something, which you should ignore, but you should think I had group 1 and group 2. And what I can do is I can take those 2 points, and now I want to run a statistical explain on those two groups. And what that does is so the geometry guides my question, but then I want to say, well, statistically, how are these two groups of people different? So we have stuff built into the software which runs statistics on the two groups that I made, and then it tells me how they're different. And I can just sort by that, and one of the ways they're different is so these are genes, these are the names for genes. They're as meaningless to me as they probably are to you, except that I happen to know where the story ends. If I were actually doing the analysis, I would be a genetic expert, and these names would mean something to me. But ESR1 is a gene that's linked to breast cancer, and it's one of the big distinguishing factors between these two groups. So I had these two, the geometry, right, started my analysis, and now I have a statistical distinction between two subpopulations of patients. Right? So I've sort of moved from the geometric world to the statistical world. And what I'm going to go do is I'm going to just color the network by ESR1. So this is what we were talking about before, which is this, I'm just taking a function, I'm just coloring by the function. So here cool values, blue, would be low values of the function, and high values would be red. I see immediately that there are two, the distinguishing ESR1, which was a distinguishing factor between these, and I see that this is a really good, right? It's high on one and low on the other. So I also have a column that wasn't used in the analysis, which is I know clinical information about these patients, which in this case is whether they died or not. And what I can see is, so these are the patients who have died. This flare here consists entirely of surviving patients. So I have a subpopulation of breast cancer patients, right, that fit into the certain profile, the certain gene profile, that are going to survive according to the study, and this is sort of verified independently of us by lots of people as well. I'm just showing you how we would do it in this system. So that's sort of how an analysis sort of typically runs for us, is we're sort of geometry guided analysis, and we get insights from our data using the geometry, and then we verify it with sort of traditional statistics for group differentiation. Okay, so that's how our software looks, and it does lots of nice nice things, I wanted to actually show you this plot here as well, this one up here. So this here is using PCA as a lens. So one thing you might hope for, which is sort of a very traditional, standard technique for data analysis, is that you could see these two flares easily in the PCA plot. And in fact, you can't. And that's sort of the power of having different lenses at your disposal. And so what happens with PCA is you're finding a linear subspace that sort of captures the maximal spread of your data and projecting onto it, right? But stuff can happen in the projected dimensions. And just to highlight that, if you look at where one of these flares is, it's kind of all over an edge in the PCA. And in fact, sort of some of the pieces that flare lives in aren't even connected or really near each other in the PCA plot. And similarly, we see the same thing with the other one. So having those lenses, having other lenses really is, it is an improvement over, you want a big selection of lenses, and they really do pull out different information. And I'll also say that this summary here, this Y summary, right, it kind of gets right to the core of a question, right? It gets right at the low ESR1, high survival group, right? It sort of, it summarizes out all the irrelevant information and just gives you exactly what you're looking for. And that's what we're looking for with a good lens selection, is that kind of thing. PCA, now there's a lot of things going on in this PCA summary here. You can see there's these different clusters, and there's all kinds of other questions you can ask about why are those clustering the way they are. But it's a more complicated picture, and honestly, I don't actually know what's going on with those clusters. Okay. So finally, I just wanted to show you a couple more use cases. So this here is online fraud. So this here is from a company that does like on fraud for large online retailers. If a transaction's fraudulent, they have all kinds of information about your browser, about your account history, about where you're accessing from, your IP address. So sort of the data is very rich. It has a lot of different kinds of data in there, right? IP information, geospatial information, browser version information, right? It's sort of a very heterogeneous data set. And so it has, you can see here, it has almost 700,000 points and 1,000 something plus dimensions. And where I've colored it right now is by the fraud score of the company that produced this data. So they have their internal model that they use, and this here is colored by that model, with red being more fraudulent. So the topology kind of says that their model isn't too bad, in the sense that we agree, their model is this nice kind of rainbow function across the topology, which says that we're sort of in agreement in a very coarse sense with what their model says. And also we've said that we've split off, right? There's these two pieces that have split apart, and we have a high, very risky group, and then kind of a mixed group. So again, we're kind of, the geometry is reflecting something. Now they built their model not using any topology. They built it, it's a complicated, sort of hand-built decision tree kind of model. But it says, on first glance, we're saying they did a pretty good job. Now, there's chargeback information in the data set. So chargeback information is ground truth for fraud, in the sense that this is when someone says there was fraud, but you didn't catch it. Right? So this is the error, like the ground truth error in the data set. And what we can see is very quickly, we're looking for systematic errors. So are there kinds of frauds that they're missing? So some kinds of frauds, like this one there that we missed, right? That's probably, you're never going to catch everything. There's a sporadic cases of fraud that sort of have no pattern, and maybe that one is like that. But we see on the tips here, there are these high chargeback regions of fraud that the company was missing. So just like we did with the breast cancer, we can run statistical explains as what's going on in those points. And we see that those people are spending a lot of time on the page, on the checkout page. They have Flash disabled. They have no JavaScript. So this was actually a surprise for the people who hand-built the models, because usually the fraud that comes with no JavaScript and no Flash comes from bots, because they want to be fast, and they don't spend a lot of time on the page. So when they tried to sort of preconceive of sort of their fraud decision models, this was just something they hadn't really considered. But it's something that sort of that systematic error pops up immediately in our analysis, and we can identify it. And they went after the fact, and they ended up thinking that they came back to us and they said that they thought that this was spousal fraud, meaning you're spending a lot of time on that checkout page because you're using your spouse's credit card sort of covertly somehow. That's what they told us. I don't understand the JavaScript and the how that fits into the spousal fraud picture, but that's what they told us. Okay, so this here is another data set. This here is acceleration information from mobile phones. So this was part of a Kaggle competition. And the question is, can you identify the Parkinson's patients? Right? The people, so there are, what's it called? No, there are people with, whatever, the controls. There are controls and people with Parkinson's in the data set. Sorry, I totally blanked there. And the question is, can you separate out using the accelerometer who has Parkinson's and who doesn't? And here we have the red are all the controls, and then the blue are the patients with Parkinson's. And actually the dominant signal didn't come from high frequency tremors. The signal that we're picking up here has to do with low frequency handling of the phone, which was a big surprise to everyone. And I think it's just it's sort of fascinating how, again, the topology just kind of pops out this distinction. Now here, this says that we have two populations of Parkinson's patients. And we have no explanation for that. And I don't, we can't say, oh, this is Parkinson's A and Parkinson's B. We're saying there's two groups based on the phone accelerometer, but we don't have like a biological understanding of that. And I don't know if, yes?
Did you look at the response function for the accelerometer? Because it may be that high frequency response has been filtered out.
That's a good point. I didn't actually do this analysis, so I don't really know what was done or how sensitive the phones are.
Could it be the Apple versus the Android phones?
These are all Android phones that were handed out by so they were given out by the people doing the study, so that there's like a ground truth in the phone. That's a.
Well, the ground truth in the phone, but if a phone was only on one person, you don't know.
That's right, and this. So I looked at this data set. So I have a little story with this data set. Before I went to work at Ayasdi. I was on Kaggle. I was looking at the data competitions, and I looked at this data set. I was like, that's ridiculous, because it's like I forget, it's like 100 gigabytes of time series information for 150 people. Or something like that, or no, for 15 people, 15. So it's 150 points here because of the slicing of the time intervals. For 15 people, gigabytes of information, I was like, this competition is a waste of time. And when I went to Ayasdi and I was talking with someone, one of the data scientists there, it was after I'd been hired, but there was like a get to know, a pre-work start get to know you thing. I was talking with a data scientist who did the analysis, Demir, and he started asking me about this competition. I was like, that thing is ridiculous. Nobody's ever going to solve that. No, it's not going to happen. And then, he's like, and there we have it. He had done it. And I personally find it really surprising. I mean, like I said, I thought that there's no way anybody is going to do anything useful with this data set. And there we have it. So for me, that right, because it didn't meet my expectations. That was really surprising. Okay, so the last one, emergency room triage model. So this here is in an emergency room looking at there's a checklist of sort of things that you fill out for like how sick a person is. And then there's a model that says how likely they are to die, and then you serve people appropriately relative to the model. So this at the top is the prediction of the model, and then on the bottom is the actual data. And you notice that there's this right away. You see that there's a systematic error right up top there of people who the model thought would survive and who were actually dying, and that we were able to, again, very quickly identify this kind of systematic, or another way of saying systematic, linking it back to the talk earlier, is the localization. Something's localized in the data set. And we were able to link back this localization actually to certain forms, certain fields not being filled out on the intake form. So, so very quickly being able to identify that kind of systematic error can, I guess, can save lives. So, okay, that's it. Thank you for having me. See, the problem with, in both cases, is that there's a lot happening in your data. So a metaphor that I like to think about is that of a room. You walk into a room full of people, and when you walk in, it's just white noise, right? There's all these different conversations happening. And what you want to do is find those conversations that are relevant to you, or in some way summarize the conversations in the room. So that's the problem with big data and with complexity, are the number of stories going on. And what we want to do is create summaries that are useful to us. So TDA on this kind of high level, this metaphorical level, is the tool that's going to summarize out the irrelevant stories to get at something interesting. And in a certain sense, I mean this in a kind of technical way, because what we do is actually we summarize the geometry, and we do that in a rigorous way. So the metaphor is reasonably deep. Okay, so this here is kind of our guiding principle at Ayasdi, is that data has shape and shape has meaning. That's the motivation for everything we do. That's how we try and approach our problems, is what is the shape of our data? How do I extract the shape of the data? What is the shape of the data? Tell me. So I'm going to focus on the second half of this and not get too much into exactly what shape means. I want to talk about extracting meaning from shape. Okay, but first, well, let's just since I've gotten this question before, well, what is shape? Let's just spend a slide describing what shape is. So I describe shape as like my one sentence that I use to describe shape, is that shape is the global realization of local constraints. So locally, there's in your data, locally in the space you're looking at, there's some constraints over what can happen, right? But those local, I'm going to talk today about topological data analysis and what we do at Ayasdi. So I have kind of two goals here that for this talk. So first, I want to show how TDA is a framework for data analysis or machine learning, sort of if you think of machine learning just as large-scale data analysis. And then I want to demonstrate specifically how Ayasdi uses TDA to help companies. And so at the end of the talk, I'd like to show you some of the actual some actual use cases from some of our clients. And so TDA encompasses a number of things, and I'm really just going to talk about the part of TDA that Ayasdi does. So there are other things that I'm not going to talk about: persistence homology, sensor networks with sheaves, things like that. But that's fine. Okay, so what we want to do is extract meaning from complex data. So we want to get insights from our data. We want to make our data useful. And I say complex because, well, data is complex because it's big, meaning there's a lot of it. So that's one way data is complex, and we deal with some of that at Ayasdi. But we also deal with a lot of data that's complex because it's feature rich. So if you think of something like genetic data, you could have SNP data, you could have 500,000 columns in the data set, and there's complicated interdependencies among those columns, among gene expression levels, among mutations, among all kinds of things. And so I don't want to think of the data problem as just being one of volume. I want to think of complexity, and complexity can come from volume. It can come from other problems as well. So, or of course both, right? You can always have both. So the way I apologize, I've been sort of indoctrinated into the corporate language, but it's just a function, and you should consider it a smooth function. So here's what we do: we take a point P, and here the way I've drawn it, I'm thinking of this function as just the height function on this data. So I take a point P in the range of the function. I look at the inverse image of P, so that's this circle here. I take that inverse image, and I'm going to draw a point on the far right here for every connected component of the inverse image. So the way I drew this here, there's just one connected component. There's just a circle in the inverse image. So I drew a point on the far right. Okay, so let's look at the point Q. Now we have two circles in the inverse image. So there's two connected components. So I'm going to draw 2 points. And that's it. That's all we're going to do. And I just go through all the points now, systematically do that. I get this Y. So this is a summary of the data space. So the data space started off as this pair of pants that has this hollow cavity. And with this function, the summary I've produced is this Y. What have I captured? I've captured the legs on the pair of pants. What have I lost? Well, I've lost all the holes, the circles, right, with this function. So that's one choice of function. Well, now I'm going to look at another function to show you how other functions will extract other summaries from the data. So this function is just this function that goes down, G. So P, look at the inverse image of P. It's this left edge. And so I'm just going to draw a point for that left edge. Moving slightly to the right, I have two pieces in the inverse image. There's this front line and this back line. So continuing on like that, I get a circle until I reach this middle point here, where again, the inverse image of a point in the middle is kind of the saddle point here. It's connected. So those local constraints sort of doesn't really create shape. Shape is what happens when you take the big picture of all those constraints, right? If you look at a circle, locally it's very flat, it looks like a line, but it's bending ever so slightly. When you take that global picture, you get the circle, and that's the shape. That's the shape of your data. So for a given problem, shape is determined by your choice of features, sensors that you're pulling data from, columns in your data if you're thinking of tabular data, properties to measure, and then a metric on those features. So that metric is the summary of what those local constraints are. So that's one way to define shape, but there are more relaxed notions of shape, and the techniques I'm going to describe to you today are going to work with those other more relaxed notions. So everything, I'll probably say this a couple more times, everything I say will work for essentially abstract topological spaces where you have some open covering of the space. So you have a set of open sets that cover the space. But to stay concrete, everything I say will be done with rows and columns. The rows are your data points, the columns are your features. There'll be a kind of metric lurking in the background, and we'll just move and then stay in that sort of concrete, more familiar world. So the goal, this is just rephrasing what I said earlier, it's to understand or summarize the shape. And part of that that's really important for TDA, which is what I think distinguishes it from a lot of other techniques, is that we have no preconceived notions of what the shape should be. So we're not doing any kind of like manifold fitting or linear fitting or anything like that. We really try and eschew the preconceived notions of what our data looks like. Okay, so I'm going to kind of step into the TDA in a couple steps. So first, I'm going to start in math world. So we're not in data world yet. So what do I mean by math world? I'm going to draw the data as a smooth manifold. So it's just going to be a smooth shape. And when I say function or lens, you should think something smooth, continuous, nice in whatever class of functions you want to consider. So that's because that's going to give you the right intuition and kind of internal mental picture. But we don't need any of these assumptions when we're actually in data world doing the analysis. All the things that I'll describe will go through without modification. Okay, and maybe even more importantly is that in the real world, data is never really sampled from a smooth manifold. Or I should say, there are certain engineering problems that are very rigidly constrained where data might be sampled from a smooth manifold or from a, maybe just a locally smooth or, stratified space or something. But in general, real data is never like this. It's kind of crazy and wild. And we should keep that in mind. Okay, so here's our data, and I've drawn it here. It's an inverted pair of pants. And when I produce here, I'm going to now kind of flesh out this picture, and I'm going to show you how we make topological summaries from the data. But you should remember that you never actually get to see your data. And the reason I'm drawing it as this nice two-dimensional manifold is so that you can concretely see exactly what is the thing that I'm summarizing, what is the topology, what have I lost, what am I saying, right? Well, you'll be able to see it all exactly, but in reality, you never get to see it. So you should put kind of a big black box over the data. Okay, so here's how we start. We start with the continuous function f, and this function f at Ayasdi, we call it a lens on your data. And I'll probably switch back and forth between saying lens and saying function, and you'll just have to bear with me. I